Okay, welcome back, guys. Going to move forward here with differential equations, just a little bit though. And so we're not going to go over any new techniques or any new solving methods like we did last class. I'm actually just going to go through a free response question with you, something that is typically seen within an AP exam and something that could definitely possibly be on this year's exam as well, as all this information is still totally valid. Even if you're not taking the exam, these are just really good questions, really good connections that you can make to some of the things that we've done in the past. And so what I'm going to do is go through this one, 2013, question 6. Technically, it only had a part A and B on the actual exam. I'm adding a C and a D just to give you a look at some of the extension questions that might be asked on other questions that you'll have to solve yourself. But the main part for 2013 that's new will be A. Okay, so that's an extension question. B is what we focused on the entire last class. So hopefully you're getting the hang of that and had some success with the homework. And then C and D are also new, although those two are very similar to one another. All right. I just want to show you what more we can do with differential equations. And if you take a look at it without even reading the question or the given information, and just looking at these questions quickly, what do I see? I see an equation for the tangent line. Okay, well, we've done something like that definitely before. Part C, jumping down here, says, looking at solution curves, are they increasing or decreasing? Okay, well, we've definitely talked about intervals of increasing, decreasing before. And then part D talks about determining concavity, which, again, we've also done. And we actually did all of this pretty much in the first semester, right? So this was everything dealing with derivatives, which I've been trying to sort of hammer that in a little bit. That differential equations, what are they? They are derivatives. They are rates of change, just usually involving two variables instead of one. So a lot of today is actually going to be maybe even a little bit of review, but just a different way to talk about finding some of these values. Okay. So let's read the question and just kind of get an idea of what we're doing. So the first part just tells us the differential equation. I noticed that I've got y's and x's within that differential equation. dy dx equals e to the y 3x squared minus 6x. And I'm also given an initial value, right? Okay, so I've got this initial value, 1, 0. Whenever we are given that initial value, typically we're going to have to find the particular solution, right? Which part B does have us do. All right. And again, remember, this originally was A and B. Typically with these questions, part B, or finding the particular solution, is the last part of the question. All right. And I'll show you, I actually have the scoring guidelines for part B here. It is worth, I think, 6 of the 9 points that could have been awarded. So the part B is definitely the big part. However, we're going to do a couple more ourselves. All right. Okay, let's look at part A. All right, so part A says, write an equation for the line tangent to the graph of f at the point 1, 0. Use the tangent line to approximate f of 1.2. So this is kind of new for us, and also kind of old. So the first part, we noticed that we're writing an equation for the tangent line. Hopefully, as soon as you read that, what would jump out to you? Y minus y1 equals m times x minus x1, right? That's the form of the tangent line that we've been trying to work with the entire year. We've said that in class so many different times at this point, so I'm hoping that is familiar to you, certainly at this point. And we are going to actually use that equation. So, but part A really asks us to do two things. Number one, we need to come up with the equation for the tangent line that specifically goes through the point 1, 0. But then I also need to use that to approximate f of 1.2. So that part's actually somewhat new to us. We've done something similar to this where we've talked about using a tangent line for linear approximation. And I'm going to sort of spell that out and maybe draw it for you in just a second. All right, but let's start with the first part, writing the equation for the tangent line. And before we move to the next slide, I just want to say one thing. This question, for whatever reason, has always trip people up because they think they're finding the particular solution. Why? Because you're given a particular point, 1, 0. And students' minds always go to, oh, well, there's a particular point. I must be solving for the particular solution. Not true, right? So unless it tells you specifically to solve for the particular solution, like it does in Part B, you're not doing that, right? You're writing an equation for the tangent line. Part A is actually a whole lot easier than Part B. All right. So just keep that in mind. As soon as you see equation of tangent line, you're not solving for a particular solution. You're writing an equation for a tangent line. All right. Let's start taking a look at the solution a little bit here. So let me cover this up just a second here, just so. All right. So like I said, what is the equation of tangent line? We know that is y minus y1 equals m times x minus x1. The very first thing that I would change is looking at m, right? So m I know is the slope of the line. Well, the slope is the derivative. The derivative is the differential equation. So I'm just going to change m to dy dx just so we know that we are going to use the differential equation that this problem initially gave us. And we're going to plug it in directly for m. Okay, and then we'll start to replace some of these x1s and y1s with actual values. But for right now, we're just trying to see the connection between the tangent line and the differential equation. I also added the y sub 1 over, okay, because eventually y sub 1 is going to become a number. And so I want an equation of a line. And so I just want y equals some value over here, okay? And so eventually this is going to look not exactly like mx plus b, but more like mx plus b. And then you'll see the equation of an actual line kind of come in nicely. Okay, so what can we do from there? Well, if I look back just very quickly, my differential equation, e to the y multiplied by 3x squared minus 6x, that's dy dx. That is the slope of all of the lines, right? Or all of the curves, excuse me, at any particular point. And so at specifically 1, 0, it will also be the slope there. And so that's exactly what I want. I want dy dx, which is the slope, to take place of the slope. And so all I did was I did plug in that differential equation. However, I did change all of the x's to x sub 1s and all the y, the y to y sub 1, because we want the exact slope, the numerical slope. And so we're actually going to be plugging a value into those. All right. They're not just variables that will stay variable. They're going to be actual numbers at this point. And then I also switched. I already did that. The y sub 1 is the same exact y sub 1 as we'll go into the e sub y sub 1, e to the y sub 1. All right. So at this point, if it helps you, certainly pause the video, right, and just kind of take a look at this sequence. Make sure you understand where these values are coming from. Make sure you understand, what's getting replaced for what pieces on each step, and then also why I changed all these x's to x sub 1s and the y to y sub 1. All right, let's move forward here. So once we do that, push down a little bit. Excuse me. From there, what do I know? Well, it gave me a particular point, 1, 0. 1 is x sub 1, 0 is y sub 1. Those are the actual values that I'm plugging into x and y. And so from there, all I'll do is I'll replace all of my x sub 1s with 1 and all my y sub 1s with 0 and pretty much solve. And from there, actually, it's pretty easy. So because the equation sort of spills itself out. So as soon as I put, 0 in for y sub 1, e to the 0 becomes 1 itself. And then inside the parentheses, 3 minus 6 is negative 3. So I just have this negative 3 that's left over in the front. And then x minus 1 stays, and then plus 0. Okay, so that goes away completely. And so here is my equation for my tangent line. Negative 3 multiplied by x minus 1. All right. So now the next part, right, I'm going to just draw something here, because if you look at this, this is definitely a decreasing line, right? So if you were to distribute the negative 3, you get negative 3x plus 3. Okay, so that's a downward sloping line that goes through positive 3 on the y-axis. But what is it actually doing? Well, it's an equation of the tangent line itself. Okay, so it hits the curve at one particular point. And so let's just say the curve looked something, and again, I don't know what it looks like, right? This is just sort of hypothetical, right? Let's say the curve looks something like that, right? And at 1 comma 0, which let's say is right here. So let's say this is the point 1 comma 0. I've got this tangent line with that represents that equation, all right? Or this equation represents this tangent line. So that is the tangent line itself. The blue line, let's say, is the actual solution curve, which we don't know what it looks like, but we're just kind of imagining that this was the solution curve, and here's that tangent line that goes through it. So the slope right there is -3. And what I want to do is, if this point right here is 1 comma 0, right? I want to use my tangent line, because I don't know the equation of the blue curve. All I know is the equation of this red line. I want to use this tangent line to approximate the output of this point on the blue curve, which is 1.2 comma question mark, right? Because I don't know what it actually is. I don't know why that dot's not staying there. Okay, well, that's a question mark right there. I don't know what this value is, right? That's what I'm trying to find. I don't know the curve, therefore I can't find outputs of the curve. I do know that I started the problem with this is 1 comma 0, right? And I was able to create a tangent line. And so I can actually use that tangent line, because I can get outputs from this now, right, to approximate the output of x equals 1.2 on the actual curve, right? And so I can find this red dot, this output right here, which again is an approximation, but it looks pretty darn close to what the actual output of the function would be, right? And so this is one use of a tangent line. If we're able to create a tangent line, we are able to approximate output values of inputs that are really close to where the tangent line actually strikes the curve, right? So notice that I'm not trying to find an approximate output for 10 or 50 or something like that. I have the exact curve, the exact tangent line that goes through 1, and I'm just trying to approximate the output for 1.2, right? Something really close, because if you look at it, the further away I get from the curve, the further away the tangent line is from the actual output. So I want to use an equation for a tangent line to approximate the output of something really close to where the tangent line actually strikes the curve. In this case, I'm using 1.2. So that's just sort of the theory behind it, or what you're actually doing, right? I just wanted to show you exactly what this question is asking you. To actually approximate is really easy, because you have an equation for a line, you know the x value that they want you to try and find the approximation at. So we're just going to plug 1.2 into this equation, right? So I have y equals -3 times x minus 1 at x equals 1.2. I'm going to replace x with 1.2 right there, right? And then I'll just solve. -3 times 1.2 minus 1 is 0.2. I get -0.6 is my answer. Okay, and that's all of part A. Okay, so hopefully that wasn't too bad, and hopefully this part makes sense up here as to why, what you're actually doing in terms of finding an approximation. Okay, here are your scoring guidelines for part A. If you were to actually do that, you get 1 point for solving for the derivative at 1, 0. That's literally just plugging 1 and 0 into your differential equation. So that's really nice. You get a point for setting up the tangent line equation itself. And then for solving for the tangent line equation. And then you get 1 point for the approximation. All right. So you're doing a fair amount of work for 3 points, but I think there are 3 easy points to get. All right, part B, I'm not going to go over a whole lot, just to spare some time, and we've also already done this, but I will show it to you. So part B was finding the particular equation that goes through the point 1 comma 0. So now you're actually finding the curve itself. And if you were to do that, we will be separating variables. The one part that I wanted to just point out, and at this point, I encourage you to pause the video and just kind of look through this solution and see if you can follow it and see if you have any questions. If you do, I'm happy to help you out. But on the left-hand side, when you bring over the e to the y, so you'll have to divide e to the y to both sides, notice that this is really e to the negative y, right? If you were to bring this up next to dy. right? So up from the denominator, you would then have to use the chain rule. Okay, so that's why you get this negative. I'm sorry, U substitution, not the chain rule. You have to use U substitution. So that's why you get that negative e to the negative y. All right, that's why this integral looks like that. On the right hand side, it's just the power rule. I think you guys will be okay with that. Okay. So again, pause the video, just kind of run through this, see if you're okay with it. Let me know if you have any questions. This little note down here is specifically because we're using a natural log, and I need the inside of the natural log to be greater than 0. Okay, so just make sure that if you're not using absolute values, you want to kind of just note that this needs to happen, right? That needs to be greater than 0 in order for it to work. Okay, let's look at parts, the new parts C and D that I put in here. So part C is asking, are the solution curves for the differential equation increasing or decreasing specifically in quadrant 2? And then we need to give a reason. So this is not a standard question, but it definitely can come up where we're using the differential equation, which again tells me all about the slopes of all the possible solution curves that go through all the points, right, in quadrant 2 that are modeled by this differential equation. I want to know if are all the solution curves in quadrant 2 doing the same thing? Are they all increasing? Or are they all decreasing? Is it kind of like a mix match? And how does that work? And so hopefully this comes to mind what we did with derivatives in the first semester, which is, well, we use derivatives to figure out intervals of increasing or decreasing, right? We used a sign chart to figure out critical points. And critical numbers. Once we found critical numbers, we tested on both sides of those critical numbers. And if it was positive, then the function was increasing. If it was negative, then the function was decreasing. And that was all built off of the first derivative test, right? So we're using the first derivative to get all that information. Well, again, dy dx is just the first derivative of whatever function I'm working with. So as long as I plug in the appropriate x and y values into this differential equation, it's going to tell me whether the actual solution curve is increasing or decreasing based off of the sign that comes out of it, right? So we're really going to be focusing on this equation that we're given. It is the first derivative already. I don't need to take a derivative. It's just given to me, which is really nice. All right. So let's take a look. For quadrant 2, what do we know about quadrant 2? Well, what we know is that for any x value, it's negative, right? Move left from 0 on the x-axis, you have negative, okay? And for those that might be trying to figure out where quadrant 2 is right now, right? It's this guy, okay, right here. So that's the one we're looking at. And so we know that all of my x values are negative, all of my y values are positive. As soon as I know that, can I get the answer from the differential equation? And most times you can, right? Because let's look at it. If we use just these two pieces of information, x is less than 0 and y is greater than 0, plug in any x value, right, that we know of into here, we're going to be fine, right? Because e to the positive value is going to be positive. E to any value is positive. So it really didn't matter whether we're using the second quadrant for y or not, but that certainly helps, right? So if all y's are positive, e to the y is positive. Plug in for 3x squared. Well, any negative x value I plug in x squared will be positive. And then I have negative 6x. Well, now if I'm multiplying a negative 6 times a negative x value, that will also be positive. So I don't even need to test any specific point here. I just need to take a look in general. If in quadrant 2, x is less than 0 and y is greater than 0, then dy dx will absolutely be positive every single time. And so since dy dx is positive, what do I know about all the values in quadrant 2? The solution curves are increasing. Okay, positive derivative, I have an increasing curve. That's it. Okay, so some of these questions might ask you to just work with the first derivative and all those things that you can be, you're given. All right. Some of them might even ask you about minimums or maximums and how you might be able to find that. You might have to test values on both sides of a point or something of that sort. And again, nothing different, just given to you in a different way. So don't get tripped up just because you're using a differential equation. You know how to do this stuff. You know what all this language means. You're good to go. All right, part D, and I said that this is really similar because it is, but it does make us do a little bit more work, because the beginning of part D says we have to find the second derivative, right? D squared y over dx squared. So that's the second derivative. So we actually have to find that. So what that means is we're actually going to be taking a derivative, all right? And we'll get into what that entails in just a second. And then the last part is similar to part C, where we have to determine the concavity of the solution curves, of the solution curve, excuse me. So this is specifically the solution curve in quadrant 3 that corresponds with x equals 3. Okay. And in fact, this could be solution curves, right? Because there could be multiple solution curves that have an x value of 3, just depending on the y, where it goes up. But we'll see that it's going to work out both ways, right? So whether this was solution curve or solution curves that corresponds with x equals 3, we'll see how we can get a reason a reason for our answer. All right, let's first start with finding the second derivative, though. Okay, so second derivative means we're taking our differential equation that we were given, right? So it's right up here, and we're going to take the derivative of it. Well, if you notice, if we're taking the second derivative with respect to x, I'm going to run into a slight problem, right? Because here's a y. Well, we've done that already, right? And so this kind of brings back something we've done again, which is implicit differentiation. So if you ever have to find the second derivative of a differential equation, then you're going to have to use implicit differentiation, okay? If there's a y value or some other variable that's not with respect to the one that you're taking the derivative to, which in this case is x. So once you notice you have to use implicit differentiation, the next thing you have to notice is that I've got two functions multiplied by one another, e to the y multiplied by 3x squared minus 6x. That means we're going to have to use the product rule. All right, so within this, we have to use implicit differentiation and the product rule. Not terribly difficult, just have to take your time, stay organized, right? Everything that we've preached throughout the year. So let's get started on it. So the first part says, all right, I need to take the derivative of your first function, right? So f of y in this case, right? So, but it's f times g, which means the product rule is f prime g plus g prime f. So f prime is the derivative of e to the y. Well, the derivative of e to the y is just itself, right? E to the x is e to the x, so e to the y is e to the y. But since I'm taking with respect to x, I need to use implicit differentiation, so I'm going to multiply that by y prime. Remember again, y prime is a derivative. What is the derivative? It's a differential equation. So eventually I'm going to change that to dy dx, okay? And then I'm going to input the differential equation again, just to give you a little bit of heads up. All right, moving on though with the product rule. Then multiplied by g. So I'll bring down my 3x squared minus 6x. That's f prime times g, right? So f prime times g right here. Then I know I'm just going to multiply by g itself. I'm sorry, f multiplied by f and then g prime. So g prime is really easy to find because it's just the product rule, power rule, okay? So 6x minus 6. Again, if at any point you need to pause the video and just kind of make sure you're getting these steps down, please do. All right, from there, the only thing I switched was what I talked about, which is y prime is equal to dy dx, right? They're both derivatives. We know the derivative is a differential equation. From there, all I did was switch dy dx and actually replace it with the differential equation. So we're starting to get a lot picked up here, but this simplifies pretty nicely and it actually makes our answer relatively easy to work with. So now, once I replace dy dx with the differential equation up here, I noticed two things. Number one, this whole piece is being multiplied by another. E to the y times e to the y times 3x squared minus 6 times 3x squared minus 6. E to the y times e to the y is e to the y squared, which is also just e to the 2y. So those two things multiplied together is e to the 2y. And then 3x squared minus 6x times 3x squared minus 6x is 3x squared minus 6x all squared. Okay, so these two things multiplied together give me this. Right? And then the second part I just left alone. Could you take out an e to the y? Yes. It doesn't prove to be helpful in this case, though. Okay, because remember, the reason why we're trying to find the second derivative, which we did, and so that's why it's boxed, right? Because that was part of the problem. But it's leading us towards analyzing the concavity of the solution curves that correspond with x equals 3 in quadrant 2 specifically. Okay. So this is enough information to get there. So look at this over here. My conclusion is going to be at x equals 3. Okay. The second derivative is always going to be positive. Well, why is that? Specifically in quadrant 2, I know that okay, sorry about that. I had to pause the video and just switch something up really quickly. I was just recognizing that x equals positive 3 is not in quadrant 2, so that part of the question actually made no sense. And so it would absolutely make sense if this question was actually given to you. Again, I apologize, just kind of making it up and trying to make it work. And then just noticed that I made that mistake. So all I did was switch it to quadrant 1. Okay, so I'm specifically looking at the solution curves that correspond to x equals 3 in quadrant 1. All right, and so this question still works. And on the actual slideshow, if you're looking at this, I did switch it to quadrant 1 in the question as well. Okay, so part D, let's determine the concavity of the solution curve in quadrant 1, not quadrant 2, that corresponds with x equals 3. All right, so let's go back to our answer. So the second derivative still stands true. That it doesn't change anything there. That process is still the same. And so at x equals positive 3, the second derivative is greater than 0 because in quadrant 1, I know that y is greater than 0. And so if x is equal to 3, look at all the places you can plug x in for. Right here, 3x squared minus 6x. This whole thing is squared anyway. So even if there was a different value than x equals 3, it wouldn't matter because it would turn positive because I'm squaring that value. But it does matter on the back end here, right? So if I plug in 3 for x, I get 6 times 3, which is 18 minus 6, which I know is positive. All right, and we already talked about the y's being positive. It doesn't matter anyway because they're e values, which are always positive. Okay, so this whole thing, no matter what y value you choose, when x equals 3, will always be positive. Okay, and therefore, since the second derivative is positive, we know that the solution curves are concave up in quadrant 1. Okay, so quadrant 1, sorry about that, apologies there, but hopefully that process makes sense, which is the big part. All right, and understanding how we can talk about concavity through differential equations. Okay, so that's it for me. So what you have to do for homework / over break are 3 free response questions, okay? And there's one from 2014, one from 2015, and then one from 2012. And you can see you get a dose of a lot of different pieces that we've worked on so far at differential equations. We're really coming to the end in terms of rounding this unit up. And if you feel really good about these 3 problems, you're in really, really good shape, okay? So each one of them is going to throw out different pieces. You will have to find a particular solution for each one of them. I know we're doing that a lot, but it's the biggest part of this whole thing. And so I just want you to see a bunch of different varieties of types of equations that you might have to find using the separation of variables. And so that's why we're doing a lot of this stuff. Okay. For 2014, you can see this is one that you have to sketch the slope field. So that's something we did and had success with, I think. Part B, there's that equation of the tangent line. You have to use that to approximate. So that's part A of the problem that we just went over. And then part C is finding a particular solution. For 2015, you can see you have to start with actually creating a portion of a slope field. So that's finding the little line segments, the slopes of the little line segments, and placing them on the coordinates that they give you. Part B, you have to find a second derivative, right? So you're going to have to use implicit differentiation up here and then replace. And from there, you're going to have to determine concavity in quadrant 2. Okay, so think about what your x and y values are in quadrant 2. And then part C is finding a particular solution. All right. And then finally for 2012, this one's, I think, pretty interesting because it's not just, hey, here's an equation, do all this stuff. It actually links it back to something that's kind of possibly happening in the real world. So it's the rate at which a baby bird gains weight. And so what I would say is if you see this type of question or a question is posed to you in this way, it is still just a differential equations question, right? They're just putting a little bit of like I said, kind of like real worldness to it. But everything that you do is exactly the same, and the way that you do it is the same. All right. So part A is interesting. It's asking you, is the bird gaining weight faster when it weighs 40 or 70? And you have to kind of go through what that means. And I'll leave that one for you to try and just kind of see if you can understand it. Part B, we're talking about the second derivative, right? So you have to find the second derivative, but then you have to use it to explain something about this graph. So that's kind of a neat twist to what we just did with the second derivative, although very similar. Okay. And then part C is using your separation of variables to find a particular solution. All right, so you can see a trend in these. They kind of start easy, and then they get to the meat of it, which is finding particular solutions each time. All right, I'll be emailing you these questions anyway, but if you want to just look at them through here, that's also fine. All right, guys, any questions, please let me know. I'll talk to you soon, and have a great day.